Welcome to this HP Expert 1 presentation. This is the third video discussing how data flows in an Ethernet environment. In the previous video, we looked at how data flows in a network containing hubs, bridges, and switches. In this video, we'll look at how data flows in a network containing routers. Let's get started. Routers are layer 3 devices. In other words, they operate at the network layer of the OSI model. Routers do not make routing decisions based on MAC addresses, but rather use IP addresses when determining out of which interfaces traffic should be sent. Routers still use MAC addresses when using Ethernet, but the decision-making process of which interface traffic should be transmitted out of is done based on IP address rather than MAC address. So in this topology, rather than using 48-bit MAC addresses, I'm going to represent a MAC address as a single character. So A is the MAC address of the first PC, and it has an IP address of 10.1.1.1. We have a router with two interfaces, fast Ethernet 00 with this IP address 10.1.1.100 with MAC address G, fast Ethernet 01 with IP address 10.1.2.100 and MAC address H. We also have some other PCs with their relevant MAC addresses and IP addresses. In this topology, we're using a subnet mask of /24, which can also be written as 255.255.255.0. For simplicity, PC A and PC C are connected to a hub, which is connected to the router on fast Ethernet 00. PC B and PC D are connected to another hub, which is connected to the router on fast Ethernet 01. The router has therefore been configured with an IP address in the same subnet as A and C, and its fast Ethernet 01 interface is configured in the same subnet as B and D. When you configure IP addresses on a router or layer 3 switch, you configure the IP address with the mask. So the router knows that a /24 mask has been used here and will update its routing table to indicate that network 10.1.1.0/24 is directly connected to fast Ethernet 00 and 10.1.2.0/24 is directly connected to fast Ethernet 01. Routers don't populate their routing tables with IP addresses, but rather populate their routing tables with networks and make routing decisions based on the network addresses rather than individual IP addresses. So the router is configured with this IP address, /24 mask, thus the routing table is updated. The router knows that to get to network 10.1.0.0, traffic should be sent out of fast Ethernet 00, and to get to network 10.1.2.0, traffic should be sent out of fast Ethernet 01. Now how would traffic flow if device A wants to send traffic to device C? Let's say, for example, that device A pings device C. So on device A, the command ping 10.1.1.2 is used. Now IP is a layer 3 technology. MAC addresses are used at layer 2. So PC A needs to have a mapping between a layer 3 IP address and a layer 2 MAC address. PC A at this point doesn't know the MAC address associated with IP address 10.1.1.2. Ethernet is a layer 2 technology and requires the use of MAC addresses when traffic is sent on an Ethernet segment. Thus, when A sends traffic onto the network segment, it needs to know the MAC address associated with this IP address. Remember, in the OSI model, each layer is independent of other layers, and lower layers encapsulate higher layers. So how is PCA going to learn the MAC address of PCC? It does this using a protocol called Address Resolution Protocol, or ARP. The first thing PCA does is check its local ARP cache to see if there's a ready and existing entry mapping IP address 10.1.1.2 to a MAC address. If there isn't an entry on the local machine, it will send out a broadcast to try and find out who has IP address 10.1.1.2. This is called an Arp request. An Arp request looks as follows. The source MAC address is A, because the frame has been sent from A. Destination MAC address is a broadcast. A doesn't know who has IP address 10.1.1.2. So an ARP is essentially asking who has this IP address. So the IP address that's being referenced is 10.1.1.2, the source IP address is 10.1.1.1, the source MAC address is A, and the destination MAC address is a broadcast. Just to reiterate, this is layer 2 and this is layer 3 of the OSI model. Now, before continuing with that example, I'd like to show you a real-world example of ARP, or Address Resolution Protocol. So on my PC, I can type the command ARP-A, and I'll see my ARP cache. My IP address is 10.0.0.3, and as you can see here, I've learnt an IP address 10.0.0.254 dynamically. There are also some static entries in the ARP cache. As an example, this is the broadcast address at layer 3 is 255.255.255.255. The layer 2 address for layer 3 broadcast is 8Fs. We have only one dynamic MAC address in the local ARP cache of my PC. So ipconfig shows me that my IP address is 10.0.0.3. That's my IP version 6 address, but we're only concentrating on IP version 4 in this example. Notice I have a default gateway set to 10.0.0.254. So my ARP cache shows a mapping of my default gateway's IP address to a MAC address. My IP address once again is 10.0.0.3. So ARP-D will allow me to delete the ARP entries in my local ARP cache. So ARP-A shows that single dynamic entry. I'll delete it again, and notice now I have no entries in my ARP cache. Do that again. Notice the entry appears because I'm sending traffic to my default gateway. So I'll do that again. ARP-A. Notice the directed broadcast address for this subnet 10.0.0.0 has been added. So if I ping 10.0.0.123, there's no entry in my ARP cache for that entry. Notice the ping succeeds. And if I look at the ARP cache, notice there's an entry for 10.0.0.123. This is another IP address on my local router, so the MAC address is the same address as for IP address 10.0.0.254. If I delete the ARP cache again, so ARP-D, notice no entries in the ARP cache, still no entries. Let's ping 10.0.0.123. Pings succeed. Look at the ARP cache. Notice there's an entry in the ARP cache now for 10.0.0.123. If I ping my default gateway 254, previously there was no entry for that IP address, but now ARP-A shows an entry for that IP address. So what's the moral of the story? Before traffic can be sent to an IP address on the local segment, ARP is required to create a mapping between a layer 3 IP address and a layer 2 MAC address. Wireshark can be used to view what's actually taking place. So what I'll do firstly is start a capture. So on my Ethernet interface, start capturing frames. I'll delete the ARP cache. No entries are found in the ARP cache. I'll now ping 10.0.254. And let's look at the ARP cache again. So looking at the ARP cache, notice that entry is now in the ARP cache, and I'll ping 10.0.0.123. So ARP-A shows those two entries in the ARP cache. Let's stop the capture. And let's look for the ARP entries. So as you can see here, a broadcast has been sent from my local device. The protocol used is ARP, and I'm asking who has IP address 10.0.0.254, tell 10.0.0.3. So at layer 2, you can see the destination address is a broadcast. The source address is my local machine. It's an ARP request. That is the ether type for ARP. And looking at the address resolution protocol or ARP information, notice we're looking for an IP address. The sender MAC address is my local machine. Sender IP address is my local machine. Target MAC address is unknown. And we're looking for IP address 10.0.0.254. Once the ARP reply came back, I'd be able to ping that device. So in the Wireshark capture, I'm now sending an echo. So you can see it's ICMP, echo or ping request, and here I got a response or a reply. Going down further, I'll be able to see the ARP request for 10.0.0.123. Layer 2 destination is a broadcast. Source is local MAC address. And we're requesting the target MAC address. In other words, who has IP address 10.0.0.123. The reply is a unicast. So the destination at layer 2 is my local machine. The source is my local router. Sender MAC address, sender IP address, target MAC address, target IP address. In this case, I was communicating directly with that device rather than sending traffic through it. So the MAC addresses and IP addresses used are my local machine and the local router. So in summary, when a device wants to communicate with another device in the same subnet, it will send a broadcast onto the local segment to find out the MAC address of the device using the target IP address. So in this case, A sends the frame to the hub. The hub, because it's a multi-port repeater, will send the frame out of all ports. So the router will receive the frame as well as device C. Network interface cards will only receive unicast traffic destined to their MAC address or broadcast and specific multicast addresses that they've subscribed to. The router has a MAC address of G on interface FOST Ethernet 00, so the router will receive the broadcast and forward the ARP request to higher layer protocols. The router will be able to see at layer 3 that this is an ARP for an IP address of 10.1.1.2, but the router is configured with IP address 10.1.1.100 and 10.1.2.100, so the router will drop the frame. Routers do not forward broadcasts, so this broadcast is not forwarded out of interface FOST Ethernet 01. It's dropped. The NIC on PCC will receive the broadcast and see that this is an ARP request for its IP address. So it will then reply with an ARP reply, as we've seen in the Wireshark capture. So it'll update its ARP cache entry to show that IP address 10.1.1.1 is associated with MAC address A. It will then send the frame to the hub. The hub will forward the frame out of all ports. The router will receive a frame with a destination MAC address of A, but its MAC address is G, so it'll drop the frame. A will receive the frame because the destination address is A and its MAC address is A, and it will then update its ARP cache with its ARP reply showing that IP address 10.1.1.2 is associated with MAC address C. At this point, no user traffic has been transmitted. This was simply to work out which MAC address is associated with IP address 10.1.1.2. The ping traffic can now be transmitted with the source MAC address of A, the local machine, destination MAC address of C, the destination MAC address learned through ARP, source IP address is 10.1.1.1, destination IP address is 10.1.1.2. When the hub receives that traffic, it'll repeat it out of all interfaces. The router once again will drop the frame because its MAC address is G and the destination MAC address here is C. So that traffic is dropped by the router. The PC will receive the traffic because the destination MAC address is C, its local MAC address is C. The layer 2 headers will be stripped and the IP information will be read by higher layer protocols. This is an ICMP packet, echo, so the PC will then reply with an echo reply. C will send a frame to the hub with source MAC address of C, destination MAC address of A. It knew which MAC address to use because of the previous Arp request. So its local cache has an entry of 10.1.1.1 associated with MAC address A. Destination IP address is 10.1.1.1. Source IP address 10.1.1.2. When it hits the hub will repeat that traffic out of all ports. The router will drop the traffic because the destination MAC address is A, not G. A will receive the frame because the destination MAC address is A once again, and its local MAC address is A, and it will send the traffic to higher layer protocols. So the ping will succeed. In our Wireshark capture as an example, I can filter on ICMP traffic. Notice the initial frame from my PC to the local router is an echo request. Once again, notice echo ping request, and the reply is an echo reply. Notice please that these are unicast frames. Unicast firstly from my PC to the local router, and then from the router to my local machine. The same information would be displayed if you were pinging another local device on the local segment. As a user, they would get a result, something similar to this, showing that the ping was successful. We successfully got a reply from that device. Now what would happen if PC A with IP address 10.1.1.1 wants to send traffic to device B with IP address 10.1.2.1? Please note that these devices are in separate subnets. We are using a /24 mask in this topology, so A is in a different subnet to B. Now the first thing the PC will do is to check whether the IP address it's trying to communicate with is in a separate subnet to itself. It does this by doing a logical AND using the network mask. So in this case, we've got a /24 mask. IP address is 10.1.1.1, trying to ping 10.1.2.1. 24 in dotted decimal notation looks like this, which means the network portion is the first 3 octets. So the local PC 10.1.1.1 compares the network portion with the device that it's trying to communicate with to check if the device is local or remote. In this case, the network masks are different, so it knows that the device is remote and therefore it needs to send its traffic to its default gateway to get to the remote device. This assumes that device A has been configured with the router as its default gateway. So the PC will firstly check if it has the router's MAC address in its local ARP cache, because it needs to send traffic via the router to the remote device, and this is Ethernet. Ethernet requires a MAC address for communication. So at layer 2, a MAC address is required. The PC has been configured with the default gateway of 10.1.1.100, but the MAC address of the default gateway wouldn't have been configured on the PC. So if there's no entry on the local PC for the MAC address of its default gateway, it will send out a broadcast onto the segment asking who has this IP address. In other words, an ARP request is done for the MAC address of the default gateway. When the broadcast is received by the hub, it will flood that out of all ports. PCC will receive the broadcast at layer 2, But when reading the layer 3 information, it'll see that the ARP is not for itself. It's for a device with an IP address of 10.1.100. PCC will therefore drop that ARP request. The router, however, will process the ARP request. Firstly, it'll receive the traffic at layer 2 because this is a broadcast. It'll read the layer 3 information and see once again that this is an ARP request for its IP address. The router will therefore reply to the ARP request. The ARP reply is a unicast. So source MAC address is G, the router's MAC address. Destination MAC address is A. Source IP address is the router's IP address. Destination IP address is A's IP address. The hub will once again flood that out of all ports. C will drop the frame because it's not destined to itself. Notice MAC address is C, destination MAC address is A, so it'll drop the frame. And in this case, it's the NIC that drops the frame. A, upon receipt of the frame, will process the frame because the destination MAC address is itself. So the layer 2 information is processed by the NIC. The ARP reply will be processed by higher layer protocols. Therefore, the ARP cache of the PC is now populated. PCA knows that IP address 10.1.1.100 is associated with MAC address G. So the PC can now send traffic to the network destined for the remote device 10.1.2.1. Source address is 10.1.1.1 itself. Source MAC address is itself, but notice the destination MAC address is the router. The layer 2 frame goes to the router. The layer 3 information contains the destination IP address of the remote host. The hub will flood that to both C and the router. C will drop the frame because it's not destined to itself. The router will receive the frame at layer 2 because it's destined to its MAC address. It will strip the layer 2 information and then read the layer 3 information. So let's look at a practical example. I'm going to capture traffic in Wireshark. So start the capture. I'm going to clear my ARP cache. So ARP-A shows that there are no entries. And then I'm going to ping hp.com. Notice a DNS resolution has taken place. ICMP messages are timing out because the HP server is blocking the traffic. But as another example, let's ping google.com. Notice pings are succeeding. I'll stop the capture. HP was using an IP address in the 15 range. So let's have a look for that ICMP traffic. So notice there's the ICMP message to hp.com. Notice the address is a 15. We didn't get a reply, but the echo was sent. What I'd like you to see, please, is at layer 2, the source MAC address is my local PC. The destination MAC address is my local router. To show you that, we can see that by typing ARP-A. Notice this MAC address 001A6D 787E30 is the MAC address associated with IP address 10.0.0.254. ipconfig, that's the IP address of my default gateway. So the traffic is going from my local PC to hp.com. At layer 3, we have local IP address, HP's IP address. But at layer 2, the source MAC address is my local machine and the destination MAC address is the local router. I'm sending the traffic to my default gateway at layer 2. If I filter ICMP traffic again, here's traffic going to Google. So source IP address is my local machine, destination IP address is Google, but notice at layer 2, source MAC address is my local machine, destination MAC address is the local router. When sending traffic from one subnet to another subnet, the layer 3 headers contain the source host IP address and destination host IP address. But the layer 2 headers contain the source host MAC address and local router's MAC address on this local segment. When it gets to the router will strip the layer 2 headers and then read the layer 3 headers to determine what to do with the traffic. So the destination IP address is 10.1.2.1. The router checks if that's a local IP address, and it's not. The router has these IP addresses, so it checks its routing table to determine if it knows where the destination IP address is. This IP address, 10.1.2.1, is on subnet 10.1.2.0, which is out of FOSS Ethernet 0.1. The router therefore knows it needs to send traffic to this host 10.1.2.1 out of FOSS Ethernet 0.1. It then checks its ARP cache. Does it have an entry for 10.1.2.1 in the ARP cache? If it doesn't, it's going to send a broadcast onto the local segment requesting the MAC address of 10.1.2.1. That will be sent to the hub. The hub will send that out of all ports. D will drop that traffic because it's not an ARP request for its IP address. B will receive the traffic, so it'll receive it at layer 2, it'll receive it at layer 3, it will then process the ARP request and send back an ARP reply. The ARP reply will be sent to the hub with a source MAC address of B, destination MAC address of the router. The router is the device that requested the IP address of the PC, and the MAC addresses on each interface of a router are different. Source IP address is the local PC, destination IP address is the IP address of FOSS Ethernet 0.1. When the hub receives the traffic, it'll flood it out of all ports. The router will process the traffic because the MAC address is its local MAC address, so its network interface card will receive the traffic at layer 2. It will then process the layer 3 and layer 4 information. It will then update its local ARP cache, saying that IP address 10.1.2.1 has MAC address B. The router can now send the original ping traffic to host B. So when the frame arrived at the router from host A, it had a source MAC address of A, destination MAC address of G, source IP address 10.1.1.1, destination IP address 10.1.2.1. When it now sends the traffic out of FOSS Ethernet 0.1, it rewrites the MAC address entries. So the source MAC address is H, the local router's interface. Destination MAC address is B, the host that the router is wanting to communicate with. Source IP address is A, destination IP address is B. It's important to realize that when traversing a router or a layer 3 switch, when moving from one VLAN to another, the layer 2 information is rewritten. The layer 3 information is left the same. But every time traffic hops across a router or is sent from one VLAN to another, the layer 2 information is rewritten. When that traffic is received by the hub, it'll flood it out of all ports. D will drop the frame because the destination MAC address is B and not D. B will receive the frame at layer 2 because it's destined to itself, and then it'll process the layer 3 and layer 4 information. In this case, it's an ICMP echo message sent from A to B, so he's going to want to reply to that echo message. So B will reply, echo reply. But please notice the echo reply is going to a destination IP address of 10.1.1.1, host A. Source IP address is 10.1.2.1, local machine. The source MAC address is B, but the destination MAC address is the router. Device B is sending the traffic to its default gateway because it also did a logical AND on the IP address, and it worked out that this IP address is on a different subnet to itself. So it's going to forward the traffic to its default gateway, and in this case we would have had the default gateway configured as 10.1.2.100. The hub will flood the traffic out of all ports. D will drop the frames once again because it's not destined to itself. The router will process the frame because the MAC address in the destination field is its local MAC address. It will then strip the layer 2 information, read the layer 3 information, and determine if it knows where 10.1.1.1 is. In this case, it does know 10.1.1.0/24 is on fast Ethernet 00, and this is an IP address in that subnet. So the router knows that it needs to forward the traffic out of fast Ethernet 00. The router will rewrite the layer 2 headers. So the destination MAC address is A. Source MAC address is G, the MAC address of fast Ethernet 00. The layer 3 information is left the same. Only layer 2 information is rewritten. When the frame hits the hub will flood it out of all ports. C will drop the frame because it's not destined to itself. A will receive the frame because the destination MAC address is itself. It will process the layer 2 information and then process the layer 3 information, and the ping will succeed in this example. Now, in some cases with a ping, you'll notice that the first ping fails, and that's because of the Arp requests and replies that need to take place to populate the Arp cache and therefore to allow communication. So don't be concerned if you lose the first ping, as it may be that the Arp caches haven't been populated yet. The important point to realize is that when you ping across a router or a layer 3 switch, the layer 2 information is updated, but the layer 3 information remains the same unless network address translation or NAT is used. When you move from one VLAN to another, a layer 3 switch or a router will rewrite the layer 2 information. So to sum up, a router is a layer 3 device. It makes routing decisions based on IP addresses. It rewrites MAC addresses. Layer 3 switches also operate at this layer. A layer 3 switch has layer 2 capability as well as layer 3 capability. When you send traffic from VLAN 10 to VLAN 20, the layer 2 frames are rewritten. The traffic is logically going through a router as the layer 3 switch implements routing capability, and therefore the layer 2 MAC addresses are rewritten, but the layer 3 information remains the same. That concludes this video explaining the flow of traffic in an Ethernet environment. I explained how devices such as hubs, bridges, switches, and routers operate and where they reside in the OSI model. I explained in a lot of detail how frames and IP addresses are rewritten when traffic is sent from one VLAN to another or one subnet to another. For more information, please visit hp.com/go/expert1.